Hello and welcome to another video. Today we're going to continue our discussion on thermochemistry by looking at yet another way to find the delta H of a reaction, or the heat, or the enthalpy of it. Now, one of the things that you might find as you go through chemistry is sometimes you can't always do the experiment, either because you don't have the means to, meaning you don't have all the chemicals or the equipment, or sometimes it's just too dangerous, or sometimes you just don't want to do it. So you always need another way to kind of find stuff. So Hess's law is another way that we can go about finding the change in enthalpy for a reaction. So a couple quick reminders. I want you to recall first the idea of what a state function is. So a state function, if you recall, is a property of a system that is determined by its present condition, not by its path to get there. Meaning it's the what, not the how. So we don't really care so much about how the change happened. We just typically care more about the fact that it did happen. So a lot of times we say that if you have something that's a change in, or like a delta, like delta H or delta T or delta time or whatever you might want to look at, that change in tells you that it's going to be a state function, because we really are more concerned with it happened, not how it happened. So if you think about enthalpy, which is the change in enthalpy, so remember that's a delta H, you got to think, is this considered a state function? Well, the answer of course is yes. And the why is because the path to change in enthalpy doesn't really matter. So what we're looking more at is like just the fact that the change happens, not so much how you got there. Now, the reason why that's significant is because it gives us some options in terms of finding the change in enthalpy. So if you don't really want to actually do the experiment, but you know that the reaction you're looking for has a series of stages that gets you there, so it's a series of reactions that takes you there, if you know the delta H's for each of those individual reactions, you can use those to sum up to come up with the overall delta H of the final reaction you're looking for. So, and the reason why that works is because it's a, now what I want you to real quick is pause the video so you can kind of write down what I have written here. It'll make it just a little bit easier to go through this example. So here's what Hess's law says. If a reaction is carried out in a series of steps, the delta H for the reactions will equal the sum of the delta H for the individual steps. So we're going to use the following reactions to determine the delta H for the combustion of methane to produce liquid water. So one of the first things you need is you need to know what are we actually looking for. In this case, we are looking for this equation right here. The CH4 gas plus 2O2 gas gives us CO2 gas and 2H2O liquid. Now you may be thinking, well, what's the big deal? We've been doing methane combustions for a while, but this one is different because it's looking for the liquid form, not the gaseous form. So the next thing you're going to see is we have two other different equations here, and both of these are written in green. So these two are what we're going to use to ultimately create our final equation that we're looking for. So now you might be going, well, what do you mean by create the final reaction? Well, we're basically going to look through and kind of cancel stuff out that we see appearing in different reactions on both sides of the arrow. And what will happen is you'll see that the things you don't necessarily need anymore will cancel out, and the remaining ones will stay. Now what that does is it'll create the final reaction for you, and then in addition you just simply add up the delta H's that you've got. So let's look at this one. So I have methane gas plus oxygen gas giving me carbon dioxide gas plus water gas. That's our typical methane combustion. And the delta H for that is a negative 802 kilojoules. So 802 kilojoules is released. Below that we have the fact that going from water gas into water liquid also releases an additional 88 kilojoules of energy. So what we can do is by canceling out the things that we see appearing on both sides of the arrow, we can create our final equation. So if you look between the two reactions, there are two things that appear on the product side of one reaction and the reactant side of the other, and that is the gaseous water. So you have water vapor here and you have water vapor here. Since that appears as a product on one and a reactant on the other, we can effectively cancel them out because we're showing that you're using one immediately again to do the reaction. Nothing else cancels out, so what you're left with by writing out all the remaining parts is you have methane gas plus oxygen gas, and that's going to yield your CO2 gas and your two waters that are now in liquid form. And if you look, this is exactly what we're looking for. These two things are the same. So we got that part correct. So now that we have our reaction drawn out, the methane to oxygen to CO2 plus water, we can simply now add the delta H's for the two reactions that we used to get there to find the final overall delta H of the reaction. So delta H is going to be equal to a negative 802 kilojoules plus a negative 88 kilojoules, which even I can do this math in my head, comes out to be a delta H, or overall delta H, of negative 890 kilojoules. This is actually the final answer we were looking for. So now we know that if you combust methane and you form liquid water instead of gaseous water, you release 890 kilojoules of energy instead. And that should hopefully make sense. If you remember, we talked before how a state change also results in either an addition or a release of energy. In the case of a gas going to a liquid, your energy is going to go down because you're going to release some. Because remember, liquid molecules move slower than gaseous molecules do. Now, there's some key things to remember. So with all Hess's law problems, the chemical reactions given must add up to that final equation. If they don't add up, then something kind of went wrong. So the key to the problems is that whatever you do to the reaction equation, you must do to the delta H value. So if we had like double any of these reactions, we'd have to double our delta H. So if we reverse the equation though, then you have to reverse the sign of the delta H. If you multiply the equation by 2, then you must multiply the delta H. So now we didn't see any of these weird things happening in the first trial that we did. So we're going to do another setup here. What we're going to do is we're going to do another example, and now you'll see both kind of things happening where you have to switch the direction of the arrow and also multiply the equations. So when you read this, we're going to find out the enthalpy of combustion for carbon to CO2 is a negative 393.5 kilojoules per mole of carbon. And the enthalpy of combustion for carbon monoxide to carbon dioxide is a negative 283 kilojoules per mole of carbon monoxide. Using this information, calculate the enthalpy of combustion of carbon to CO. So the very first thing we have to do is let's identify what are we actually looking for. So which one of these reactions is going to be our final, the one we're trying to add up to? Well, in this case, it's the very last sentence, which says that we want to know if we take carbon and we send it through combustion with oxygen to form carbon monoxide. Sorry, I already started balancing that. What is the delta H? So that's what I'm looking for. So the next thing you're going to do is write down the equations that they gave you. And I'm going to use a different color. So let's go with green. So in this case, I have two reactions I'm working with. One of them is the reaction of carbon with oxygen to form CO2. So I'm going to write that one down. Solid carbon plus O2 gas gives us CO2 gas. Of course, we need to balance that, which it looks like it is. And the problem tells us that the delta H for this reaction is a negative 393.5 kilojoules. Now we're going to write the next equation they gave us, which is when you take carbon monoxide and you send it through combustion, so again with oxygen, to form CO2 gas. Again, we've got to balance it, so we need a 2 in front of the CO and a 2 in front of the CO2. You get an overall delta H for this reaction of negative 566.0 kilojoules. Now you might be wondering, where did I get the negative 566 kilojoules from? When you look at the numbers, that number doesn't appear anywhere. Well, if you read it, it says the enthalpy of combustion of CO to CO2 is negative 283 kilojoules per mole of carbon monoxide. And I have 2 moles of it, so I had to double it to get there. So these are the two reactions we're going to use to ultimately get to our final reaction. So we're going to want to cancel anything out that we can that isn't necessary in the equation. Now the problem is, if you look here, nothing's going to cancel out right now. Like, we have oxygens both on the reactant side, which is great. We want those there, but we have these two CO2s both as products, and we don't want CO2 anywhere. Not to mention the fact that I want carbon monoxide to be a product, not a reactant, which you see in reaction number 2. So the first thing I always suggest on these is flip around any of the reactions that you need to. So I'm going to take the second reaction, and just so it's different color, and I'm going to flip it around. So I'm going to reverse its direction. So instead of being carbon monoxide plus oxygen to give me CO2, I'm going to write it as 2 CO2 gas breaks down into 2 carbon monoxide gas plus O2. So all I do is I flip the reaction around. I switch the arrow. Now since I switched the arrow, my delta H has to go from negative 566 to being a positive 566, because as we've discussed before, if you reverse the flow of a reaction, the enthalpy has to switch also accordingly in terms of sign. Now I'm going to go ahead and scribble out this other one just so I don't get confused and think that there's 3 reactions. So great. Now I've got my CO2s on opposite sides, so they're going to cancel, but we still have a little bit of a problem. Because if you look in the first reaction, I only have 1 CO2 molecule, whereas down in the second reaction I have 2 of them. I need to get them to cancel out completely, so now I'm going to multiply my top reaction by 2. So if I'm multiplying that by 2, that means I have to multiply all the coefficients by 2, and I've got to multiply my energy by 2 over here. Now if you look, the 2 CO2s are going to cancel out just nicely, so I can cancel those out. And if you also look, I have one oxygen over here on my product side where I don't want it. But luckily, I have two oxygens up in this reactant. So the two oxygens cancel out there, giving me just one oxygen in this first reaction. And in the second reaction, it cancels out completely. So in the end, what you end up with, everything is canceled out. I just bring it down. I get my two carbons plus my one oxygen molecule, yielding my two CO molecules. And if you look, this is the same now as this one up here that we were looking for. To find the overall delta H, all I'm going to do is add the delta H's from the two reactions. Now, since I have a multiplying for this first reaction, I got to remember to take the negative 393.5 kilojoules and multiply by that 2 before I add it to the other 566 kilojoules from the second reaction. When you do this, the overall delta H for this reaction comes out to be a total of negative 221.0 kilojoules of energy. So that's a lot of stuff to remember. One of the things I want you to keep in mind is that you can manipulate reactions, you can multiply them, or you can switch the direction of them. Theoretically, you could divide them also if you needed to. If you have too much in one of the reactants in terms of coefficients, you could always divide by something to get them smaller as well. What I want you to do before you do anything else, though, is always see which reactions you have to flip around first. That way you can get everything on the correct sides of the reactions. You get the things you want as products over on the product side, the things you want as reactants on the reactant side. So what I want you to do is give yourself a trial here. If you look down at this next problem, here's one that's a little bit more involved, a little bit more challenging. So I want you to go ahead and try it. So pause this video and then come back to it in a couple minutes and you'll be able to check your answer. Okay, so here's the answer. Hopefully this is what you found right here. Look good? Real quick, just to kind of recap what I did here. So remember what I said before is that any reaction that you need to flip over or flip around in direction, you should do that first. So that's what I did right here. This was the very first thing I did. And you can cross this out to kind of see it. I went through and flipped the reaction around so I could get the B2H6 on the product side where I needed it to be. The second thing that I did then was I went through and kind of figured out if I had enough of the other reactants and products to get everything to cancel out that I didn't need anymore. So as you can see, my second step was I went through and figured out that I had to divide this first reaction by 2. So you can see that I divided all these by 2 to get my reaction coefficients set up correctly. And then I remembered I had to also divide the final delta H to get that in there also. I then noticed that the second reaction also didn't have everything it needed to, and I found the easiest way to do that was to multiply those all by 3/2, which is where you got all these numbers from. Once that was finally done, I was able to go through and see that a lot of this stuff all cancels out now. So like all my oxygens are going to cancel out because of the 3 O2s over here. My B2O3 cancels out because I've got B2O3 on this side. Remembering I reduced it to 1 there. And then if you also notice, the waters are going to cancel out because I have 3 waters in this reaction, 3 waters here, and all that's left then is the remaining things, the boron, the hydrogen, and the B2H6 that I needed. Then it was just a matter of adding all together all the delta H's, remembering to divide by 2 and multiply by 3/2 to get my final answer right here. So this is by far one of the more complicated types of questions you might see with Hess's Law, but it gives you a good idea of how all the different moving parts can work together. Hopefully you have a pretty good handle on this now. We will talk about this more in class. We'll do some more practice with it. Make sure you write down questions you have, but please make sure you look back over these examples and we'll talk about it in class. Catch you later.